at the position and also update the global map of this environment. After that, we can have the cognition part. That means we can plan the path or assign some tasks to the robot. So the path will be generated based on this cognition process. And then the robot actually should control the actuator. So this is the motion control part. And the robot moves. And we face the new real world environment, and then again and again we iterate this process. Perception, localization, cognition, motion control will be iterated all the time. And as you might already know, localization is one of the most important things we should solve in operating the robot. So this is the where am I problem, where am I? So to localize the vehicle, we usually use the odometry from the, for example, if this is the wheeled robot, as you already have, the model robot will be utilizing the encoder to update the position of the robot. So that method is called the odometry or the dead reckoning. So we can somehow predict the position, but it is very uncertain because there can be some slippage or we face some uneven terrain. In that case, it might have a lot of errors in the odometry. So based on this predicted position, and if you have the map in advance, then we have the map database, and based on this predicted position, we can somehow predict where the objective or obstacle lies. So based on that, if you have the sensory observation, then we can match them together. Yeah. At the predicted position, there should be something like this, but in the actual map, in the actual map, you can have some prediction, but actually we can observe something different. So there can be some discrepancies, but we can somehow match them together. So if they match together, then we can update the position of the robot. So estimation will be updated, and the position will be updated, and it will be fed back. And if the robot moves again, then we utilize this encoder information to update the position. And also we have the new observation, so we match them together, and again we update the position. So this will be iterated over time. So we will discuss how we estimate the robot position based on wheel odometry. So we assume that we have the two-wheeled mobile robot like this. Left wheel and right wheel over there, and we have the encoder information over there. So we can somehow estimate the distance traveled using the left wheel and right wheel. So x, y, theta, we will estimate this information. Yeah. This is the global coordinate, xi. I means the initial coordinate or inertial coordinate. This can be the world coordinate, actually. So based on this world coordinate, we should estimate x, y, position of the robot, and the heading angle, theta. Theta is usually measured from this direction, counterclockwise. This is the positive direction. So we want to update the position P prime based on P, the previous position, using some delta x, delta y, delta zeta should be added, and that will be the updated position. So we can use the odometric information. That is the delta SR, delta SL. This is the distance traveled by the right and left wheels. So using the encoder information, we can measure this one using the sensor information. And this is called the baseline length. This is distance between the two road wheels. So using that information, we can update the position. Delta x, delta y, delta zeta could be obtained. Because using the simple geometry like this, delta x could be obtained by using distance traveled, cosine, then we can have the delta x, distance traveled, sine theta, then we can have the updated delta y. Yeah, delta s is the average distance traveled on both, using both wheels, average distance. So delta s cosine theta will be delta x. So we have the fine tuning like theta plus delta theta over 2 because we have the little increment of the theta. So we also have the average because from 0 to delta theta, the angle will be varied like that. So we have the average change of this angle, delta theta over 2. So you can have the delta x. Delta y, likewise, we can have the sine term and we can obtain delta y. Delta theta could be obtained easily. The difference between the traveled distances between these two wheels divided by the baseline length, then we can obtain delta theta. So that's the final equation. Yeah. XY theta is the previous position and orientation, and we add the incremental distances and the incremental angle change. So it is called the kinematic equation of the differential drive robot. And we should have the covariance model, error model of the wheel encoder. So wheel encoder will be very uncertain because as I already have mentioned, there should be some kind of uncertainty due to the uneven terrain or some slippages or some unexpected disturbances. We have some kind of error. So that error will be proportional to the traveled distance. So KL will be some constant multiplied with the traveled distance on both wheels. Delta S R, delta S L, their absolute value multiplied with some constant. That will be the uncertainty. Uncertainty from both wheels will be modeled like this. But how do we get the uncertainty of the P prime? Sigma delta is easy to handle because we already know this information. We already measure this information using the field encoder, so it is easy to obtain. But how do we obtain the uncertainty of the P prime? So we can start from here, P. And some uncertainties from delta SR, delta SL will be here. And also delta theta will have some uncertainty due to delta SR, delta SL. And we should add the covariance with the new covariances generated by this odometric movement, and then we can obtain the new covariance. So that will be obtained by error propagation law. So you may already know about this one. If you have learned about the engineering mathematics, you already know about this one. So you can also visit this Wikipedia, propagation of uncertainty. So if you have the probabilistic distribution of the variable like here in the x, and if y is the function of x, this is very nonlinear, as you can see. And this uncertainty will be propagated to y based on what? Based on the Jacobian, actually. F sub x is the Jacobian of variable x. So we can just multiply Jacobians in front and rear of this original covariance matrix. Then we can obtain the covariance matrix of y based on the previous covariance matrix. So error will be propagated based on these Jacobians. That is the uncertainty propagation law. So you can use this law, but it is quite simple, as you can see in this Wikipedia. So if you visit this website, you can see mathematical illustration how we can obtain that. So if f is ax, this is the linear equation, then you get the covariance of x by using this conventional equation. Expectation x minus mu squared. You know that. And if you want to find out sigma f, sigma f, then by definition, it is the expectation of f minus expectation of f squared. So if you unfold this equation, then you obtain this. A x minus mu multiplied a x minus mu. So you can see that A will be in front and A transpose will be on the rear side of sigma x. So sigma x will be transformed to sigma f by using A and A transpose. This is what happens in the linear equation, f is equal to ax. But how about the nonlinear equation? So we are dealing with the nonlinear equation like this. We can linearize this nonlinear equation using the Jacobian. So J is the Jacobian, and around the operating point, F0 is the operating point, we can linearize. So this is Taylor series expansion actually. You can have the Taylor series expansion, and you know that F0 is constant. This is the operating point, this is constant, and it does not contribute to error on F. That means we just ignore this. You can just ignore this term. So that's what happens. So F will be modeled using Jx. This is approximated by Jx. So this is the linear equation again. So you have this equation, J sigma x, J transpose. So that's why you multiply the Jacobians on both sides of sigma x, then you can obtain the sigma y. Do you follow me? So we first calculate the Jacobian. Jacobian is simply the gradient. Gradient around each variable, x1, xn. Then you can obtain Jacobian like this. This is matrix. You can simply put the matrix in front and rear side, and then the error will be propagated based on this law. So we will utilize this one to obtain sigma p prime, because sigma p will be propagated to obtain the sigma p prime, and also this term will contribute to the error propagation also. So we start from here, covariance of delta, sigma delta. So this will be proportional to the distance traveled on both fields. So we have p plus something, delta x, delta y, delta theta. So the error will be propagated like this. Sigma p will be propagated based on the gradient with respect to p, and sigma delta will be propagated based on the variable delta r and delta is r and delta is l. We calculate the Jacobians and multiply them together and combine them, because we have the p plus delta x, delta y, delta theta to obtain p prime. So the remaining thing is to obtain the gradients like this. We can simply obtain those partial derivatives and we put them 3 by 3 matrix will be formed, and also delta is r, delta is l. With respect to those variables, we take the derivative of f, then you can obtain this 3 by 2 matrix. You follow me? Then the error will be propagated automatically. So we have used this one, the original equation, p plus delta x, delta y, delta theta. So with respect to x, y, theta, we take the derivatives. With respect to delta is r and delta is l, we take the derivatives, then we can obtain this. So to achieve the localization, given the prior map of this environment, we perform this one. Given the position estimate, previous position estimate p k by k, this means the position of position at time k based on the Kaist measurement. And each covariance sigma p for time k, the current control input UK, this will be obtained by the odometry information, that means the encoder information from the wheels, and the current set of observations gk plus 1. So at the new time k plus 1, we obtain the new measurement. So g is the new measurement, and the map is given, and k is given. And then we want to compute the new position estimate, p k plus 1 bar k plus 1. K plus 1 means the new observation is obtained. We incorporate that observation and find out the new position at time k plus 1. This is called the posteriori information, posteriori estimation, and its covariance. So P's covariance will be obtained like this, sigma P, k plus 1 by k plus 1. And anything unclear? Do you need some clarification of the symbols in here? No? So we have two phases, prediction and perception. Yeah. Prediction, at the prediction phase, the robot starts from x0. The robot is assumed to be here at first. And this information is known. As the robot starts moving, uncertainty grows due to the odometric error. So as I already mentioned, there are some kind of uncertainties in the odometry due to the uneven terrain or fuel slippages. So at first, if the robot is at x1, then it has some kind of uncertainty, and it will be the probability distribution like this. Some kind of uncertainty here, but if it travels like here, because we can measure the UK is the control input, that means we can obtain this information from the encoder, field encoders, then the robot will be in x2. This is pk plus 1 bar k. We did not incorporate the observation at, but we still can estimate somehow the position of this robot at time k plus 1. This is called a priori information. So you can see that the covariance of this position will be dispersed. Yeah? More covariance, as you can see. Covariance will be growing if the robot moves like this. And the next stage is the perception stage. Exteroceptive sensor like the laser rangefinder or the vision sensor will be used, and it will measure the distance d from the wall. So it will measure the distance like here, distance like here. So this is the actual distance, d is the actual distance, and d hat is the estimated distance. So if you're assuming that the robot is in here at x2, and if there is a map like here, we know the obstacle is here, so if the robot is here, then the estimated measurement will be d hat. Yeah. But actually we have obtained the d using the sensor, actual sensor. So there is some kind of discrepancy between them. Yeah. It is expected to have d hat, but the sensor returns this different distance d. Yeah. So we have some conflict. So we have to fuse these two measurements. Yes. This is expected one, and this is the actual one. So by fusing them together, we can obtain this information, x2 to 5. So this is the final estimation. That is denoted as pk plus 1 bar k plus 1. So we have incorporated the new measurement at time k plus 1, new measurement d at time k plus 1, and obtained the estimation of the position at time k plus 1. This is called a posteriori information. Yeah. So a priori means we have not incorporated the measurement yet. A posteriori means we have incorporated the measurement now. That's the difference between them. So how to fuse these two? Yeah? This is the uncertainty, estimated uncertainty at x2, but we had the actual measurement like here, and we fuse these two measurements to obtain this one. And you know that this estimation will have small covariance. Then this one or this one. Now, this always happens. If you have the previous two measurements and if you fuse them together, then you get always the better result. So we get more refined position information by utilizing this scheme. So from the field encoder information, we predict the measurement of the position, measurement and the position information of, this is called the odometry. This is done by using the previous kinematic equation, this one. This one is the kinematic equation. So you can use that to predict the position at first. And at that position, you can have some prediction of the observation. The measurement should be D hat. But actual observation indicates that we have the measurement of D. So there can be some discrepancy between them, but still can match them together because we know that these two information should be the same. So using this matching, we can fuse them together and update the position. So this will be iterated over time. This is another example. The robot starts from here and there are three pillars and the red one indicates the probability of the robot. Probability of the robot in here. So at first it is the flat distribution. Now we don't know which location the robot is. And the robot proceeds on the right side and observes the pillar at first. Then we have three peak probabilities like here. The robot will be here or here or here. Because we know the map already. If the robot observes those pillars, one of them, then the robot will be in front one of them. And if the robot proceeds again, then this probability distribution will be dispersed because we have uncertainty growing. So growing uncertainty, we have some flattened probability like this. And again, we observe the next pillar right here. Then what happens? Among these three, this only will survive. How about this one? The robot has proceeded like here, but we are observing this pillar, but in here there is no pillar. So this probability will be cancelled. And also this one, the robot is proceeding here, but there is no pillar, so this probability should be decreased. So we only have this peak at this correct location. This is the map-based localization scheme, and also called the Markov localization. But Markov localization is not easy to handle because we need a lot of computation time because we have to update all the probabilities around all the positions. So it is not easy. Computationally very, very consuming. So to approximate this Markov localization, we can introduce Monte Carlo localization. That means we use set of particles to approximate the probability distribution. So rather than describing the probability using continuous variables, we can introduce discrete variables using the set of particles, and their probability will be updated over time. Then it will be time efficient and will be very fast. So we distribute the set of particles and we calculate the weight of each particle. The weight is actually the importance probability of this particle. And the weight is updated over time and resampling process will be applied. That means if the particle has more weight compared to others, then it will have the higher probability of survival in the next phase. So this will be iterated over time. Then, if time goes, we will have more and more good particles as time goes on. So this is also called particle-based localization or Monte Carlo localization. In short, we call it MCL. And the previous fusion-based method is called the Kalman filter-based localization. We introduced the Kalman filter to obtain more refined result as time goes on. So the concept of the Kalman filter is just the fusion of the previous observations actually. If you have two measurements like Q1 hat and Q2 hat, so this is the Q1, we have some measurement like here, Q2 in here, they have the sigma 1 and sigma 2, standard deviation sigma 1 and sigma 2, and we want to find out the best estimate based on this Q1 and Q2. Which one will be best estimate these two measurements? So Q hat, we want to find out this Q hat. So how to find that? We have the weighted least square method to find the most optimal one. So Wi is the weight, and Q hat minus Qi squared, and sum them over, and this will be defined as the error metric, and we want to minimize this error. How to do that? To find the optimal one, we can just take the derivative and set it to 0, because this is the quadratic equation. If you take the derivative and set it to 0, then we can find out the optimal. So, take the derivative with respect to Q hat and set it to 0, then you can find out Q hat with respect to Q1 and Q2. So the solution is like here. Q hat is equal to something Q1 plus something Q2. And you can see that this is the linear interpolation of Q1 and Q2. And there is W1 over W1 plus W2 in front of Q1, and in front of Q2 there is W2 over W1 plus W2. And you can set W1 and W2 based on the sigmas. So if you have large sigma, then it means we have large uncertainty, so that is less important. So we can decrease the weight. If you have small covariance, then we have large weight on that. Yeah. So using W1, W2 like this, if you substitute that, then you can obtain this result. So this result will be very, very important. So from the previous measurement, Q1, if the new measurement comes in, Q2, then you can just simply multiply this factor, and with the difference between Q1 and Q2, then you can update Q1 to obtain the most optimal Q hat. This is very, very, very important result. So this is the Kalman filter actually. So if you plot that, this is the sigma 1 at Q1. At Q2 we have sigma 2, and if you fuse them to obtain Q hat, then you can see that sigma is always less than sigma 1 and sigma 2. Because we have this one. If you have sigma 1 and sigma 2 in here, then Q hat will always have less sigma. So Kalman filter is very, very similar to the previous formula. So X hat is the previous estimation, and if the new observation comes in, and their difference will be multiplied with some factor, and will be added, then we can find out the optimal one. Very, very similar. Yeah. The previous estimation and the new measurement and the previous estimation, we can multiply some factor here, k. K is called the common gain. Then we can find out the optimal one. So in terms of sigma 1 and sigma 2, we have the same formula like here, and sigma will be updated like here also. And you can see that the sigma will be formulated like here. That means sigma will be always less than sigma 1 or sigma 2. Because we have this relationship, always less. So the fusion always induces better result. Fusion of the previous two information, we get always better result. So formally, we can have the current filter for these systems. So this is a dynamical system. Xk plus 1 is equal to Fx plus Gu plus V. V is the process noise. Y is equal to Hx plus W. Y is the measurement, and W is the measurement noise. H is the measurement matrix. F is the process matrix or system matrix. G is also the matrix multiplied with the UK. UK is the control input. That is, in the mobile robot, we can obtain this information from the encoders, both encoders. So this is the process model, and we have some uncertainty. Also in the measurement, we also have the uncertainty. So this illustrates the dynamical system. And we assume that we already know this property of V and omega, V and W. This is the zero mean, white Gaussian noise with known covariance matrix, like Q and R. We set these two parameters in advance. And also F, G, H already known. Yeah, already known. And current filter is a recursion that provides the best estimate of the state vector X. X can be the position information, for example, X, Y, Z. So we have three steps in the current filter. First, prediction based on the last estimate. Because we already know F, G, H, we can estimate that. So X hat and Y hat could be obtained, but until now we don't have the observation incorporated in this equation. So that's why we have bar K. Bar K. Given the measurement at the time K, we want to estimate the position at time K plus 1 and the measurement at time K plus 1. And this is very important that you should drop this V and W because they are random noises. We set it to 0. We set it to 0 in the prediction part. Second, calculate correction based on the prediction and the current measurement. So this is the prediction X hat, and this is the actual measurement. So based on that, we can calculate delta X. Finally, we can update the prediction. So delta X will be just added with the A prior information obtained in step 1, and then we can obtain A posteriori information at step 3. Very, very simple. Yeah? You can just predict based on the equation provided, like this, and calculate delta X. Just to simply add it, and then you can have the optimal estimate of X. So this is the Kalman filter. This is automatically done if you just follow the Kalman filter equation. So this is the Kalman filter equation. Prediction step, observation step, update step. We start from initial condition, X hat 0 by 0. We assume that we already know the initial position, and P 0 by 0. This is the covariance matrix. So we already know about this one. We set it to, for example, identity matrix. So we start from there. We already know F, H, Q, Q, R is already known. Their covariances are already known. So we have the known information right here. So we substitute this initial condition. And also, P0 by 0 is known, so we substitute this one here. Then first, we estimate, we obtain the field encoder information. That means we have the control input. So we can calculate x hat, y hat, p using this formula. And then we have the prediction of the measurement, y hat. Yeah, y hat is obtained. And pk first 1 by k is already known by using this equation. So you are given these two in the step 1. And then we calculate innovation based on the actual measurement and the predicted measurement. So their difference is called the innovation term. So this innovation term mu will be obtained and it will be used in the last step. And also each covariance, innovation covariance, will be also calculated based on P and H is already known and R is already known. So using that information, we can obtain this innovation covariance. And we have the measurement. And the last step is the update step. We calculate the common gain. Common gain is obtained by the previous information like P, K plus 1 by K, and H is already known, and S is already known, so each inverse will be multiplied. Then we obtain the common gain. And based on this common gain, we will just multiply this common gain with the innovation term. Mu was already obtained, so we multiply it with the common gain. This is delta x. Delta x is simply added to the previous a priori information, then we can obtain the posteriori position estimate. And P is also updated, like here. So using those formulas, it will be iterated automatically. So it will be iterated as time goes on. This is the Kalman filter for linear system. But what happens if you have the nonlinear system? In the nonlinear system, you can just have the approximation using the Jacobians. This applies when we have the linear system like here, but if you have the nonlinear system, then you should use the Taylor series expansion using the Jacobian. So that's what happens in the extended Kalman filter. Extended Kalman filter means we apply the linear Kalman filter to the nonlinear system. We also utilize the same equations, but you can use the Jacobians. So instead of just f, we use the Jacobians with respect to x. So jf will be obtained. And also measurement will be also we calculate the measurement Jacobian like here. So we utilize these two Jacobians, and the last thing is the same. So we just use the Jacobian over there. So you can see that the last thing is the same, except we use the Jacobians instead of the linear matrix. That is the extended Kalman filter. So based on the prior map information, we can utilize this Kalman filter to estimate the position and orientation of the robot. So that is the localization part. But we want to build a map autonomously also. How to build a map autonomously? So this is the SLAM problem. So starting from the arbitrary initial point, the mobile robot should be able to autonomously explore the environment with its onboard sensors, build the appropriate map, and localize itself relative to this map. So this is the SLAM problem, as I already mentioned in the previous slide. So in the previous slide, we had the localization part. So from the encoded information we predict, and also using the real observation we match them together and update the position. So this was the localization part we have done in the previous slide. But now we have to update the map. We have to build the map. So this part is the map building part. So if they match together, if the new observation and the previous information is matching together, then we can refine the feature parameters, feature location. If there is no matching, then we have two choices. First, is this unexpected observation? Then we should add this one as a new feature in the map. Otherwise, this is the unobserved prediction, so this is the spurious one. So we will remove these features or decrease the credibility of this feature. If we repeatedly match this feature, then we will increase the credibility of this feature. So this is the map building and maintenance route. So using this routine, we can build the map. The map will be, for example, the position information of the landmarks or the features. Z hat is the position information, and sigma is their covariances. C is the credibility factor. So we can increase or decrease this credibility factor, and if the feature is below some credibility factor, then we can remove them from the map. So that's what happens in the SLAM. So the map will be represented like here. G hat, the position information of the feature. Sigma, covariance, GT is the credibility. CT will be updated using this formula. So you can see that NS is the number of matched predictions. So if you have more and more matched features, then this NS will be increased. That means exponential minus term will be decreased, credibility will be increased. If N sub U will be increased, that means we have more and more unobserved predictions. So this is the spurious feature. So we have to decrease the credibility. If it is increased, then this is exponential plus something, so it will be increased. 1 minus this term, increase the number, so we have the decreased credibility. So we can control the credibility based on those two factors. But you can design the new one. This is one of the possible candidate solution. So now the system vector should be including the position information of the robot as well as the landmark information, feature information from the environment. So XR, X of R is the robot position information, XY theta. X1, the position information of the landmark 1 or the feature 1. X2 up to X sub n. We have n landmarks, then we have those lengthy state vector. And the covariance matrix will be also very complex, getting very complex. So SLAM actually started from very early years, like 1985. And this term appeared in 1995, and the first SLAM approach appeared in 2001. It's about 25 years ago it first started. That was the birth of EKF SLAM. Using the extended current filter, they solved this SLAM problem. And using the particle filter or Monte Carlo localization, they solved the SLAM problem. So that name is the fast SLAM. And also nowadays we mostly use the graph-based approaches, like SLAM, smoothing and mapping, incrementally smoothing and mapping, and so on. So there are several branches like here. there are a lot of feature-based SLAM. So we extract some features like the corner points, or the lines. Those features are extracted, and based on those features, we perform the SLAM. There are a lot of approaches like here. And also map-based SLAM. We use the set of particles to estimate the position information of the robot. And graph-based SLAM, this requires a lot of computation time because we perform some graph optimization, but it will output more accurate and reliable result than the previous ones. So we can classify them as the filtering based or graph based. So previous approaches like EK SLAM is the filtering approach, and they only calculate the current of poles. And we have the linearization because we are using the Jacobians. That means we linearize the problem around the operating point. But the graph-based one, we can solve all robot poses. That means starting from the initial position up to the current position, we actually adjust all the previous positions. It requires least mean square approach, and we have the nonlinear optimization. But it is quite robust because it utilizes the previous information also. But in the filtering approaches, it is very fast, but it only focuses on the current information, so it is very fragile. If there is some kind of force matching at some time, then it will diverge. But because it uses a lot of information, starting from the time zero up to current time, it utilizes all the information, optimize them together, so it is quite robust. This shows the history of SLAM. So graph-based approach, filtering-based approach, they separately evolved, but commercially available products like the cleaning robots, they mostly use the filtering approach because it requires less computation time compared to the graph-based approaches. This also shows the evolution of the various SLAM approaches. And nowadays, you can see that we can utilize the LiDAR, visual, inertial, and joint data. For the leg robot, we have the joint sensor, so we can incorporate all the information and get the very accurate result by fusing all the information. So our lab has developed those blue world-faced approaches like LVAQ. So this shows another formulation of the SLAM. So we start from XT, and we can formulate the robot trajectory like from X0 to XT, and we have the control input U sub T, and the map of this environment from M0 to M sub N. So this is the landmark information, and using the set of all observations from G0 to GK, we want to estimate the position of the robot and the landmark information from the environment. So this is the first SLAM problem. So we utilize all the possible information, all the control input, all the measurement, all the information is incorporated, and we can estimate X from 0 up to T. And also all the landmark information is obtained. This is full SLAM problem. And online SLAM problem only concerns about the current level pose. So we want to estimate X sub T only. we are not concerned about the previous locations, but we focus on the current location update. So this shows the graphical representation of the SLAM problem. So the robot starts from x0 and goes to x1, x2, x3. And we have the control input of u0, then the robot will be proceeding to x1. At x1, we have the control input u1, and the robot will go into u2, and so on. And also at x0, we have some measurement like g0 to g5. And they will create the landmark information like m0, m1, m2, m3, m4, and so on. And at the position x1, we also have the observation like g6, g7, g8, but you can see that g6 is matching with m2. Yeah, m2. So this was previously measured, and we again measure this information. Then we can fuse this information, two information, and get more refined result. So this shows the graphical representation. So full graph optimizer, we utilize all the information. Yeah, from x0 to x3, we wanna adjust all this information using m0 up to m8. So we optimize all this structure. Yeah. But if we have a large number of landmarks, then optimizing this one will be infeasible for real-time SLAM. So if you have a full graph optimization, another name of this graph optimization is bundle adjustment. So we can information can move backward in time. Best possible estimate given the data and model could be obtained, but computationally demanding. It is difficult to provide online estimate for a controller. So if we require the real-time performance, then we need to sparsify the SLAM graph. So we need to prune some parts of the SLAM graph. This shows the filtering approach. So filtering approach only focuses on this x3, disregarding the previous information like x0, x1. So EKF, extended count filter, will solve this one. So this shows the structure of the EKF. Very simple. Yeah. XV is the vehicle location, XY theta, and P1 to Pn indicates the feature location. Yeah. Landmark location. Feature and landmark are the same. So feature location P1 up to Pn will be also estimated. And how will we estimate them? Using the kinematic equation FV, UV control input, we can update this vehicle position. We already know that. And the landmarks should be stationary. We assume that the features extracted from the environment are stationary. They are not moving. Yeah. So non-moving features are extracted, and based on that, we can update this information. So that's why we introduced the identity matrix. Yeah. This will not vary over time. Only the vehicle information will be evolving over time based on the kinematic equation. Very, very simple one. It appeared in 2001. This is the first EKF SLAM approach that solved this problem. But as you can see, watch it. Yeah. Very, very simple. Put identity matrix in here, put 0 here, and put this landmark information here. This was the key idea. Yeah. In addition to axis of V, we incorporate these landmark positions in the state vector. That was the idea. Instead, we assume that these landmarks are stationary. We put identity matrix. And if you solve this one iteratively using EKF, then it will also correct the landmark information because they are correlated. In a single matrix, there is f sub v and also identity matrix in here. So if we iteratively apply the EKF, then these feature locations and the vehicle location will be correlated and feature locations will be also updated over time. So that's the big idea, actually. So the convergence was proved for linearized model, but there is some computation burden because this requires n by n matrix inversion. As we already have seen, in the EKF there is the S inverse matrix, innovation covariance inverse matrix that requires n by n matrix inversion. So if you have a very large number n, for example 100 landmarks, then we should perform 100 by 100 matrix inversion. That's impossible. To do it in real time, it is almost impossible. So this requires a lot of computational burden. So it is not suitable for online use for huge number of landmarks. 1,000 by 1,000 matrix inversion. Have you ever did that? Yeah. It's almost impossible. So that's why the people moved from EKF SLAM to particle-based SLAM, and also nowadays graph-based optimization-based SLAM. But basically, EKF SLAM is quite important because we have to know the principle of SLAM. So EKF SLAM summarizes all present experience in the extended state vector, comprising of the robot pose XD and the portion of the all features M sub I in the map and associated covariance matrix. So if we have the 2D lines as the feature, as the landmark, then the size of this measurement will be 3 plus 2n. Size of the state vector is 3 plus 2n. 3 is for xy theta, and n is the number of landmarks, and because this line could be explained by using the distance and the angle information. So we need two variables to describe this line. So that's why we have 2n. So the size of the covariance matrix will be 3 plus 2n by 3 plus 2n. The actual state vector will be like this: x, y, theta, and alpha 0, r0. This is for the first line. Second line, alpha 1, r1, up to alpha n-1, r n-1. So all the robot moves and makes, as the robot moves and makes measurement, yt and pyt are updated using the standard EKF equations. So the last thing is automatic. We have the Kalman filter equation, so you can just substitute this one to the Kalman filter equation, then it provides the most optimal estimate. So in the prediction, we can just use the kinematic equation we have seen in the previous slide. So you have the previous position and the orientation, and we utilize delta S cosine theta, delta S sine theta, and delta theta will be added, and we get the prediction of the position at first. This is prediction step. But during this step, the features are unchanged. We assume that. So that's why alpha is not updated. So 0, 0 will be added. We assume that they are stationary. And the covariance will be propagated using the error propagation law, as we already discussed. This was previous covariance. And using that, we multiply the Jacobians in front and back, and they will be propagated. So you can compare the localization and SLAM. In the localization, we are only concerned about obtaining x, y, theta, they will be updated using the EKF equation. But in the SLAM, the difference is that we incorporate the landmark information in here, landmark information, as well as x, y, theta. We have alpha hat, r hat, like here, landmark information. But it's very simple because we add 0. So that's the difference between localization and SLAM. But as you can see, SLAM is quite simple. There's very small changes, like here. There's very small change. We only think about how to update this landmark information. Using this error propagation and also using the current filter equation, it automatically updates the position of the robot and the position of the landmarks. In the measurement prediction, we have some estimation right here. So this is the estimation function. Alpha hat, r hat could be obtained using the estimation function. And G is the real, actual observation. So their difference is the innovation. So using this innovation, multiply the common gain, we just add this term to the previous state vector. Then we get the updated state. And the covariance will be updated using the common gains like here. So you use the standard Kalman filter equation. So innovation covariance, common gain could be automatically obtained using the previous Kalman filter equation. So we again revisit this Kalman filter recursion, prediction, observation, update. We already have seen that. So in the prediction, we just incorporate the kinematic equation, and the measurement equation is incorporated, so we have the estimated measurement. And in the observation, we have the actual measurement and estimated measurement, and the difference is the innovation term. And in the update step, we obtain the common gain. In here, the symbol is changed. The large W sub I is equal to K sub I. So I'm sorry for the change of the notation, but they are the same. Common gain. Some textbooks use K, but some textbooks use W. So it may be confusing, but we should note that they are the same. So we first obtain the common gain. So common gain multiply the innovation term, we just have the delta x. So we just add this one to the previous a priori estimation, then we get the posterior estimation like here. And one thing to note is that in the prediction step, the covariance will be growing because we multiply F and F transpose, they are the Jacobians, they are multiplied in front and back. It is something like the square term, so it will be growing because Q is always positive. So it will be growing over time. So P is growing at the prediction step. What about the P in update step? So P will be having like this, W transpose. It is something like the square term. So it will be decreasing the covariance. So in the prediction step, the covariance will be increased. In the update step, the covariance will be decreased. So increasing, decreasing, increasing, decreasing. It will be converging finally. So we have the convergence theorem for EKF SLAM. So map covariance matrix will be converging. That's the result of this theorem. So as successive observations are made, the map covariance matrix will be decreasing monotonically. And in the limit as successive observations are made, the errors in the estimated landmark location becomes fully correlated. And in the limit, the absolute location of the landmark map is bounded only by the initial vehicle uncertainty. So as time goes on, if you have multiple observations and if you apply the Kalman filter successfully, then the map covariance will be shrinked, and the only uncertainty we can have is the initial uncertainty. The rest of the uncertainty will be diminishing. That's the theory. So this is the example. This is the car park environment. This is the parking lot, and there is some kind of wall and some poles here. So poles will be detected, and it will be regarded as the features. So circles means the pole locations. So they are detected, and also there are some walls, as you can see. So this is the environment. And we have the vehicle kinematics like here. This is the car-like vehicle. So the vehicle will be governed by this dynamic equation. X dot, Y dot, Z, T dot. Orientation will be governed by this equation. So this is given. All the dimensions we know, L, A, B, they are known in advance. So using that, we can predict the next position of the vehicle. Measurement equation, we use the 2D LiDAR, and 2D LiDAR actually measures the distance to the object. In here, the object is the pole. So we extract the pole location using the LiDAR sensor. So this is the pole location, so we measure the distance, and also the angle can be measured. So using these two information, we can set up the measurement equation. That's it. We have the prediction equation and measurement equation, and the rest of the thing will be done automatically by using EKF. The only thing you need is to provide the Jacobians of this one. Yeah? Jacobians of this matrix, Jacobians of this matrix, then you can run this EKF automatically. So this shows how it works. So we start from so this is the predicted position. So estimated path shows the predicted position, and we observe the three landmarks. Yeah. Three poles are expected, and blue star means the beacon location. Beacon means the landmark locations. So you can see that actual plot using the LiDAR data, and its ground truth location will be somewhat different. There can be some kind of small error like this. So by incorporating those measurements, we can obtain these vehicle locations quite accurately. And at this time, you can see that until now, there was some kind of error. There was some error right here, but at this time, we observed some landmarks again. So that's why we have some decreased uncertainty. So we have decreased error, and it follows quite well. Okay, so this is the example you can have. So as I already mentioned, we can have the Bayesian-based approach or graph-based approach. Bayesian-based is also called the filtering-based approach, and graph-based optimization-based approach. So we are only concerned about the current log poles in the filtering-based approaches, but in the graph-based approaches, we are concerned about the full trajectory. So if the robot starts from here, and we have multiple observations like here, and this is the current pose. So using all the information gathered from start from time 0, we gather all the information and optimize all the information. Then we can estimate the full trajectory from time 0 up to time t. It requires a lot of computation time actually. Nonlinear least square method should be applied. So we can illustrate this problem using this graph. So the robot starts from x0, proceeds to x1, proceeds to x2, and so on. And at each time we have some measurement, m0, m1, m3, they are the landmarks. And this can be modeled using the nodes and edges. Yeah? Those robot positions are considered as the nodes, so node x0, node x1, and so on. And their measurement or estimation is modeled using the springs. So if you have the odometry, then it is quite uncertain. So we have the soft spring, soft constraint. But if you have the LiDAR measurement to obtain this M0 measurement, then this will be quite strong spring, very steep constraint. So we have the soft constraint and hard constraint, and we can form this node and edge graph. And at this location x6, we again observe M0. Then what happens? We have very strong constraint in here. That means using this strong constraint, we can modify these previous locations, x5, x4, x3, x2, x1. They can be adjusted to optimize those relationships. So this is something like the configuration, finding out the configuration with the minimal energy in this problem. Do you understand? So usually this steepness is modeled using the covariance. If you have the small covariance, that means it is very reliable. Yeah. If you have the small covariance, then it means it is the reliable constraint. That means we can connect them using very strong spring. Yeah. If you have large covariance, that means it is not reliable. That means we have very soft spring. You can model this steepness using such kind of covariances. So in this example, we utilized all the information. Node and also landmark position, they should be connected all together. So this is quite complex. So the original formulation was like here. The robot was in x0, x1, x2 up to xm, and at that time we have the control input U1 to um, and also we had a measurement from G1 to GK, and using those measurements we have the landmarks. Yeah, quite complex. So the people had the idea, we can transform this one to very simple graphical notation like here. Because if you have observed the L1 twice at x0 and x1, we can have the relative transformation between x0 and x1. Yeah? We know this relationship. Yeah? The distance, angle, we know that. Also at this location, distance and angle, we know that. So using this information, we can somehow infer the relationship between x0 and x1. The transformation between x0 and x1 is estimated, and this will be directly used as a constraint. Then we can remove those landmarks. We can drop out all this information. Then we can have this simple graph called pose graph. We only have the poses. We don't have the landmark information. So that's why we call it pose graph slab. using this pose graph, we can optimize this graph, then we can recover all the position information. Do you understand? So this will simplify the computation. So you can see the mathematical formulation like here. Originally it was utilizing L in the measurement estimation equation, but now we do not have L. We only have load information, xi, xj. Using that, we have the prediction of the relative transformation between them, and if we have the actual measurement and compare this one to this predicted relative transformation. That's the difference. So using that, we can easily we can transform the original SLAM problem to more convenient pose graph SLAM problem and solve this one quite easily. So you formulate this pose graph, and the remaining thing is to optimize this pose graph. How do you optimize this one? So we have the x is the pose vector of the full trajectory, so we want to solve this x. G is the relative pose between two nodes, Gij. This is the relative pose. Relative pose means relative distance and relative orientation. So those information is Gij, and H is the prediction. Where H is? H is the predicted relative pose between node I and node J. So their difference will be regarded as the residual. This is something like the innovation term. So in the pose graph optimizers, they call it residual. Residual of the predicted and observed relative poses between two nodes. And we also use the lambda I, large lambda I. This is the measurement information matrix. This is the inverse of the covariance matrix. So we utilize that matrix. So R transpose lambda R. Because we have to consider the covariance. If the covariance is small, then it is very reliable information. If covariance is large, unreliable information. So inverse of that covariance is multiplied in here, and we want to minimize this one. Then after solving this nonlinear equation, we can obtain x star, the optimal pose of the robot, optimal trajectory of the robot. Okay. So if you are interested in more details of this one, then you can visit this website, GTSAM. GT is actually abbreviation of the Georgia Tech. It was developed from Georgia Tech, from USA. So they developed this library, GTSAM. So you can visit this website and you can obtain the C++ library as well as the MATLAB toolbox. You can download the MATLAB toolbox and try to run this example at first. Then you may easily understand how to use this library. This MATLAB is the actual wrapper around the C++ library. So inside this library, all the things are implemented in C++. This is only the interface. MATLAB is only the interface. Okay, so this is also the open source SLAM software. So you can visit the website and see some legacy algorithms like here. And this also shows the links, website for the SLAM libraries. But in your experiment, I heard that you will use CARTOSLAM. So that will be based on the graph-based SLAM. and that was already implemented, so you can just use that for your own purpose. So if you install those packages, how to slam, then slam algorithm will be running very smoothly. You don't have to care about the inside of this cart slam, but it solves everything. But the principle is that you are using this postgraph slam. Okay, that's it for today's lecture. Any questions for today's lecture? So you may have had the first experiment. You have your own mobile robot and they have installed the ROS over there and also installed the SLAM also? Not yet. So the TA will tell you about how to install the SLAM packages over there and have some experiment. And I heard that in the previous semester there was little problem in the SLAM. So you can easily solve this SLAM problem using the installed packages. And the real problem was, I heard that the manipulation part. It was not easy. The manipulation part was not easy. I heard that. Okay, if you have further questions, then you can reach me by email or ask the TA about your questions. Any further questions? No? Okay, thank you, and have a nice experiment. Okay.
We went back to dorms and then I have dinner planned with Z and Amir. Oh. Z? The big Y Z. Is he also from reception?